Hello. Today I will discuss about the eccentric connections where load is lying in the plane of joint and using weld connection. Here basically fillet weld will be used for connections. Now, in case of load lying in the plane of joint, two type of forces means stresses will come into picture on the weld. One is due to force, means direct force, which will be the shear stress will come into picture. One, another is will come due to eccentricity, and the stress will come due to moment. So, we have to make calculation of the stresses due to direct force and due to moment, and then we have to find out its equivalent forces, that means resultant forces, and that resultant forces should be less than the weld strength. If the resultant forces is less than resultant stresses is less than the weld strength, then our design criteria is okay, means design whatever we have designed, we have proposed is okay. Otherwise, we have to go for means increase of the weld size or length of the weld size or orientation, means the weld length and width has to be changed, and then again we have to redesign it. So, coming to this picture, if we see here that basically if there is a force P, then moment will become here as a P into E, this moment will come, and also the P as a concentric force will act here, P and P into E, right. Now, because of that the stresses will be generated on the weld. Now, if weld is connected in this way, say in the bracket, throughout the bracket if it is connected, then we have to find out the CG of the weld group, that means CG of the weld group we have to find out. Once we find out the CG of the weld group, then we can find out what will be the force stresses acting on each portion of the weld. Say for example, in this point stress will be acting, one stress will be acting in this direction vertically downward due to direct force, and another will be 90 degree to the radial distance from CG to this point, it is 90 degree, right, and then we have to find out the resultant, right. Now, again same thing may happen here, we can see that this will come here and this may come here. So, we have to find out the resultant here, but we know the stresses will develop much more at the extreme point, bending stresses. So, the radial distance of this point and radial distance of this point, if we compare, it will be more here, that means the critical point will be this point. Similarly, critical point will be this one, and this point will be same, because this distance and this distance are same, it is symmetric along this direction. Therefore, the radial distance between these two will be same, the angle between two forces will be same. Therefore, the stresses, the resultant stresses at this point and this point will be same. So, at any point if we any of these 2 points if we calculate, then we can find out the critical stresses of the section, right. So, in place of calculating entire weld length, in place of calculating in different position of the weld, if we calculate only one point, then we can find out the critical strength. So, critical strength can be found only at this point, means will be developed only at this point because of its position. Now, let us find out the direct shear stress due in the weld. We can find out direct shear stress. So, direct shear stress in the weld we can find out from this formula, that is PS. Say if I make, this will be total force P by L into T, right. Say for example, if we draw this figure whatever we have seen, and this is a column which is connected by weld. The bracket is taking a load of P, right, and this distance is suppose some distance E1, and this we have, this distance we have. So, we can find out the CG of this distance, and then we can find out the eccentricity E. So, we do not know what is the M value right now unless we know the CG of the weld group, right. So, weld if it is made through this periphery, then total length here, this L is the length of weld, will be, if we consider this as x and this as d, then 2x plus d, right, and T is the throat thickness of the weld. So, shear stress in the weld due to direct force will be P by L into T, and stress due to bending, as we told that because of eccentricity bending will come into picture, moment will come into picture. So, stress due to bending, if we write Pb, this will be M by Ip into R. R is the radial distance and M is the moment which is calculated as P into E. Now, this E, unless we know the distribution of the weld, we cannot find out the value of E, because E is not this much. E is the distance between load and the CG of the weld group. So, we have to find out the CG of the weld group, and CG of the weld group we can find out if we know the distribution of weld, otherwise you cannot be able to find out the CG of the weld. So, before calculating the stress, we have to provide certain distribution of the weld, then we can find out the CG of the weld, then we can find out the stress, how much it is coming due to moment. So, here IP is basically polar moment of inertia of the weld, and this can be calculated as IXS plus IYY. That means moment of inertia about x-axis and moment of inertia about y-y. So, IP, the polar moment of inertia, can be calculated. Then the resultant stress PR can be calculated as PS square plus PB square plus 2 PS PB into cos theta, right. So, because as we have seen earlier, so if this is a weld connection, then if this is the CG, so this is PS and this is PB and this is the theta, right. So, the resultant force PR, this is PR, resultant force PR can be calculated as square root of PS square plus PB square plus 2 PS PB cos theta, where theta is the angle between these two forces. And for critical condition, developed stress should be less than the permissible stress in the weld. So, this PR value, when we are going to calculate, once we calculate, we have to see this PR value is less than the permissible weld strength of the material, means of the section. So, if this PR value is not less than the weld strength, then we have to change the design criteria. Design criteria change means either we have to increase the length of the weld, or we have to increase the thickness of the weld, means size of the weld. Either of these two we have to do, and then again we have to check. So, with this theory we will go through one example. This example, let us see. This is the example. So, a bracket is subjected to a load of 50 kilonewton and is connected to a stanchion by welding. So, this is a column and is connected to a bracket, and it has a load of 50 kilonewton, and weld distribution has been given. So, this is the distribution. Okay. This portion is welded. Now, this distance is known, that is 150 mm, and this is 100 mm, right, and this distance is, this length is 200 mm. This is 150 mm, and let us make point A, B, C and D. Now, as I told at the beginning, we have to find out the CG of the weld group, right. CG of the weld group we have to find out. So, how to find out CG? So, along vertical direction CG will be, means this distance will be 100, because this is symmetric, but along, this is y, say suppose, but along this direction say x, that we have to find out. So, that can be found out. So, if we take a moment along this direction, means along this line BC line, along BC line if we take a moment, then we can find out the 2 into, means total area will be 2 into 100 into T plus 2 into 200 into T. This is the total area of the weld, into x will be equal to 2 into 100 T into 50. So, from this I can find out the value of x, that is coming 25 mm. That means, after taking moment along BC, we can find out the value of x, right. So, now we can find out the eccentricity. Eccentricity will be how much? It will be 150 plus 100 minus 25. That means, it will be 225 millimeter, right. Now, we have to find out the value of Ixx, value of Ixx. So, Ixx value we can find out, that is 1 by 12 into T into 200 cube for this portion. For BC portion Ixx will be this, then plus 2 into 1 by 12 into 2 into 100 T into 100 square. This is for this portion. Ixx of this area is 100 T into 100 square, because this is 100, this is 100 AR square. We are ignoring the moment about its own axis, about x axis, right, because that will be much less. T is very less, thickness of the weld is very less. So, 1 by 12 into T cube into 100 will be much less, that is why we are ignoring that value. So, we can find out the value as 2.67 into 10 to the power 60 millimeter to the power 4. So, similarly, IYY value we can find out. IYY value will be 200T into 25 square, means AR square for this portion, right, plus 2 into the horizontal portion 1 by 12 into T into 100 cube, and then to bring it to its CG 2 into 100 T into 50 minus 25 square. So, this is we are getting IYY as 4.17 into 10 to the power 5 T, right. So, IXX and IYY we can find. Now, we can find out the polar moment of inertia. Polar moment of inertia is nothing but IXX plus IYY. So, if we put this value 2.67 into 10 to the power 6 plus 4.17 into 10 to the power 5 T. So, this will become 30.87 into 10 to the power 5 T, right. So, polar moment of inertia we can find out, and total area of the weld will be 2 into 100 plus 200 into T, 2 into 100 T plus. So, this will be 400 T, and maximum radial distance we can find out. This will be the maximum radial distance. So, this R we have to find out. This R will be square root of this distance is how much? This is 100 and this is 75, because this is 25, right. So, R we can find out as square root of 100 square plus 75 square. So, that we can find out as 125 millimeter, right. So, now once we find R, we can find out the PB value. Okay. For getting the maximum shear due to bending, first we have to find out the moment. Moment will be P into E. So, here E we found, P is 50 kilonewton and E is 225 millimeter, that means 11.25 kilonewton meter. So, maximum shear stress due to bending we can find out, that will be PB. PB will be M by IP into R. So, if we put those value of M, this is Newton millimeter, IP is 30.87 into 10 to the 5 T into R is 125. So, maximum radial distance, maximum stress due to bending will be developed. So, that if we calculate, we can find out 455.54 by T, right. So, 455.54 by T will be the maximum shear stress due to bending. Similarly, I can find out direct shear stress. Direct shear stress will be how much? That will be PS. PS will be P by A, that means 50 into 10 cube. This is load by area is 400 T. Total area of the weld is 400 T. So, this will become 125 by T, and here cos theta will be 75 by 125 cos theta, because if we see the distance, this is theta. So, cos theta will be, this is 125 and this is 75, right. So, this can be found as 0.6. So, the resultant stress PR I can find out, that will be PB square plus PR square plus 2 PB PR cos theta. This value will be, if we put this value, we can see this 455.54 by T square plus 125 by T square plus 2 into 455.54 by T into 125 by T into cos theta 0.6. So, this will become 539.88 by T, right. So, PR, the resultant stress at this extreme point will be 539.88 by T Newton per millimeter square. Now, this resultant stress has to be less than the weld strength. Now, strength of weld I can find out. Strength of weld depends on the weld material, and whether it is shop weld or at site, depending on that gamma MW can be calculated, means can be used. So, if we assume shop weld, then strength of weld we can find out Fu by root 3 gamma MW. If we put the value, it will be root 3 into 1.25. So, that is becoming 189.37 MPa. That means, we can equate that 539.88 by T is equal to 189.37. So, from this I can find out T is equal to 539.88 by 189.37 is equal to 2.85 millimeter, right. So, size of the weld I can find out now. This is T means throat thickness. So, size of weld will be S is equal to T by 0.707, that means 2.85 by 0.707. So, that is coming 4.03 millimeter. That means, size of the weld we have to provide as 5 millimeter. Okay. So, from the calculation we can see that size of the weld is coming 5 mm. Now, from minimum and maximum criteria, means what should be the minimum size of weld, that from the codal provision we have to find out, and then we have to see whether it is exceeding or not. If it is less than the minimum, then we have to provide the minimum one, otherwise this we can provide, right. So, for this case the minimum thickness will be 3 mm. So, we can provide 5 mm thickness, size of the weld as 5 mm we can provide, right. So, now if it is say suppose this, in this example, if size of the weld is given and the distribution is given, then also we can find out what will be the load carrying capacity of the weld joint. The reverse way we have to do. That means, first we have to find out the strength of the weld, then according to the size of the weld we can find out what is the PS and PB, then from that we can in a reverse way we can find out the load acting at a particular distance P, that also we can find out. So, either of the way we can find out, right. So, the weld joint, when load is lying in the plane of joint, then how to design the joint, that has been discussed today. In next class we will discuss about the load acting perpendicular to the plane of joint. There how the stresses are developed, that we will discuss, and then we will see how to find out the resultant stresses and how to design a particular joint. Thank you.